Hello everybody and welcome back to my crash course in formal logic. This is an exciting lesson. We're going to start propositional logic, including symbols and functions. So this is going to include a lot of material. Hold on to your hats, okay? Now, Aristotle thought that logic should be about categories and their relationships to one another. There's an alternative to this view. Chrysippus of Soli was a Greek Stoic philosopher who thought that instead of being about categories, logic should be about propositions and their relationships to one another. What's the difference? Consider this. Categories do not take truth values, only propositions do. If I were to say to you true or false, elephants, well, that can't be true or false, obviously. Neither can the term mammals be true or false. If I say to you elephants are mammals, then you have a proposition. That can take a truth value. And elephants are reptiles, by way of contrast, may take the opposite truth value, but again, we're dealing with propositions at that point. So when Aristotelian logicians and people doing category logic use letters, they tend to designate categories, all A or B, some P or Q. Those P's, Q's, A's, and B's stand for categories. When you do propositional logic, you designate entire propositions with these capital letters. Now, after Chrysippus and Aristotle, what happened? Well, we're going to have to do a little review of history. Well, the truth is, apart from the work of Leibniz, until the time of Frege, nothing really seemed to happen in logic. Aristotle dominated logic until the time of Frege and Russell and later Wittgenstein. Let's talk about these individuals for just a moment. Now, Frege was a German mathematician and philosopher. He was a mathematician who thought that he could reduce mathematics to deductive logic, which would allow him to show in logic which mathematical proofs worked and which mathematical proofs did not. That's called logicism, by the way. He needed more than Aristotle because Aristotle's system is just not powerful enough to prove all the proofs of mathematics. He's also responsible for meeting a young Wittgenstein and sending Wittgenstein to study with Bertrand Russell. For our purposes, remember, he helped develop the concept of a truth function. Now, Russell, by way of contrast, was an English philosopher. He could appreciate Frege because his nanny actually was a German-speaking lady. German was his first language, and he was also an expert mathematician. So, being an expert in math and speaking German, he could understand and appreciate Frege. Also, he was a logical atomist who believed that the truth of a system of thought depends on the truth of its components. And when we start to build up the truth of compound sentences from the truth of the parts, you'll understand the importance of that for logic. Also, he's important for developing quantifiers, which we'll study in another class. And then we have Wittgenstein, one of the most important philosophers of the 20th century. He was sent by Frege to study under Russell, and he developed two systems of philosophy in his life, hence the early and later Wittgenstein, and he developed the concept of truth tables early on. He even referred to logic as the scaffolding of the universe. So you might want to look at the truth tables that we study and notice that they actually do look like scaffolds into which little truths fit. But that's a subject for later. Now let's talk about validity. In both systems, Aristotle's system and propositional logic, validity is a matter of form. However, in the context of propositional logic, form recognition is facilitated by operators or connectives. We're going to learn 5 of them. The first is the tilde. It's a negating symbol. It means it is not the case that or it is false that. You have a dot, which means and. A wedge, which means or if you prefer either or. You have a horseshoe, which means this implies that. We just say if then. And we have the triple bar, which is the equivalence symbol. We're going to study each of these in detail. Now, simple statements are statements that don't contain any other as a component. For example, famous people tend to be rich. Mark Twain wrote Huckleberry Finn. Paratroopers must overcome fear of heights, and Socrates was a philosopher. You just represent those with those capital letters we mentioned just a second ago, F, M, P, or S. Why did we choose those? Well, because they make the proposition easy to remember. F can be famous people tend to be rich. M can be Mark Twain wrote Huckleberry Finn. P, paratroopers must overcome fear of heights. S, Socrates was a philosopher. It's really kind of subjective what letter you choose to represent the entire proposition. Now, compound statements contain at least one other symbol as a component. It's not the case that money grows on trees. New York is on the East Coast, LA on the West. Either the Democrats will win or the Republicans will win. If every person contributes just a little, we can end world poverty. We'll resort to war if and only if all peaceable options have been used. Now notice, I'm marked in the black, some connectives here. We're connecting propositions. There's several propositions here who can take a truth value. We can say with the first case, it's not the case that M, money grows on trees. New York on the east and LA on the west could be N and L. Democrats will win or Republicans, D or R, and so on and so forth. Now, when we abbreviate these further, we can use our connectives and make form recognition even simpler. Tilde M or N dot L, and so on. And these sorts of things will help us locate the general form of an argument that we're examining. Now let's take some notes on the negation symbol, the tilde symbol. There's ways you can and cannot use this particular symbol. For one thing, you can't put it behind what it negates. You have to put it in front. And you can't use it to connect two propositions. It is our only one-place connective that we have. And you can use it immediately after an operator. For example, G dot tilde H means G is true and H is false. And you can use it to negate a compound. The last example says it's not the case that both G and H are true. This brings up an important concept, the concept of a main operator. The main operator is the operator that governs the most components in a sentence. In the first example to your right, it's the dot. Basically, you have a conjunction of the claim that G is true and H is false. In the second example, it's the negation. We have a negated compound sentence of G dot H. Most of my students don't have trouble spotting the main operator, but if you ever do have trouble spotting it, remember, it never has a set of parentheses around it. In the first example, this dot does not have a set of parentheses around it. However, neither does the tilde in the first example. So, point number 2, if two operators have no sets of parentheses enclosing them, the negation is not the main operator. The only way the negation can be the main operator is like in example 2, when it stands outside of a set of parentheses. Now, these statements are all negations, and I invite you to use the rules we just studied to try and figure out why the negation is the main operator. Typically, it's because it has no set of parentheses enclosing it. Now, parentheses are important because they distinguish between different interpretations of a sentence. A dot B wedge C is not clear. It's ambiguous between A and B are true or else C is, or else you could mean A is true and also you get either B or C. These are not the same things. Consider the following example. A, Lois Lane can fly. B, Batman can fly. C, Superman can fly. The first interpretation with the parentheses around A and B is true in virtue of the fact that C is the case. The second, where A is asserted to be true and also B or C, is false because Lois Lane can't fly. Now, when you translate sentences from English into symbolism, watch out for things that will help you out. Watch out, for example, for commas. Lois Lane can fly and Batman can fly, comma, probably means the first two propositions go together. And watch out for words like either or both. Either Lois Lane can fly and Batman can fly, comma, or Superman can fly. We could at least have used a comma there. It brackets off those first two propositions as things that need to go in parentheses together. And watch out for a single predicate in conjunction with one or more subjects. For example, Lois Lane and Batman can fly. We have two subjects, Lois Lane and Batman, combined with the predicate can fly. That's another dead giveaway. They belong in parentheses together. Well, now that we've talked about parentheses, let's talk about tildes. In this expression, the tilde affects only the A. A is false or else B is true. In this expression, since it comes right in front of a parentheses, the tilde affects the entire expression on the inside. You need to distinguish between those two cases. So it's not the case that A or B is a little bit ambiguous. Let it be the case that you treat it as governing the tilde as governing the A. The rule is negations govern only what immediately follows unless you have reason to interpret it otherwise. That's a good translation tip. Now let's talk about the dot. When you have the dot, it translates and, also, but, however, yet. Emeralds are green, for example, and rubies are red. E.R. Emeralds are green, but rubies are red. It still asserts two propositions, E.R. and emeralds are green, however rubies are red. Same difference. So whenever you have these sorts of translations, the English textbook translation is always both and. Both emeralds are green and rubies are red. Little grammatically awkward, yes, but that's the standard translation. Now, be careful. Superman and Batman are heroes is a compound. It means Superman is a hero and Batman is a superhero. Now, Batman and Superman are allies has the same grammatical structure, a predicate assigned to both Superman and Batman, but don't translate that as two sentences, Superman is an ally and Batman is an ally, because you lose the implication that they are allies of one another. Now, all these statements are conjunctions. I invite you to look through each one and figure out why the dot is the main connective, but notice it is enclosed by the least amount of parentheses in all cases, except for the first, and in the first case, it wins by default. Now, the disjunction or the wedge translates either or unless, for example, the Democrats will win or the Republicans will. Either the Democrats will win or the Republicans will. Democrats will win unless the Republicans win. Unless the Democrats win, the Republicans will. It's all D, wedge, R each case. Now, the textbook translation is always either or. Sometimes that can be grammatically awkward, but not in this case. Either the Democrats will win or the Republicans will win. D, wedge, R. Or, in this example, it's snowing in Aspen or in Golden. Either it's snowing in Aspen or in Golden. It's snowing in Aspen unless it's snowing in Golden. And unless it's snowing in Aspen, it's snowing in Golden. The textbook translation in each case is going to be either it's snowing in Aspen or it is snowing in Golden. And either or connecting two distinct propositions. You could abbreviate it A, wedge, G very easily. Now, all these statements are disjunctions, and I invite you to go through and look and figure out why the wedge, as opposed to other connectives like the tilde, would be the main connective in each one of these cases. Now, here's a good point at which to mention DeMorgan's rule, named for the 19th century logician Augustus DeMorgan. He discovered that a negated conjunction, tilde s.t in parentheses, is equivalent to a disjunction consisting of two negations. And in a similar way, if you have a negated disjunction, that amounts to a negation of, or a conjunction rather, of two negated sentences. We're going to go into more detail on this when we discover more about natural deduction, but it's worth noting here for translation's sake. Now we come to one of the most difficult connectives, the material implication or horseshoe symbol, translating if then, only if, in case that, given that, and many, many others. The textbook translation is always going to be if this, then that. If antecedent, then consequent. There are two parts. This is sufficient for that. If sufficient conditions are met, other conditions necessarily follow. If you have trouble remembering this, here's a little mnemonic device for you. Some people like to use the acronym SUN. S implies N. Sufficient conditions imply necessary conditions. Antecedent implies consequent, but this helps you remember sufficient implies necessary. Now notice, this is not an equivalence claim. P implies Q is not the equivalent of Q implies P. It's the only connective that we've gotten so far where you can't swap out one for the other letter and get an equivalent claim. Position is important with this connective. So all these statements are conditionals, and the main operator is the horseshoe. Go ahead and take a little moment to familiarize yourself with the reason why. The horseshoe is enclosed by the least number of set of parentheses, no sets of parentheses essentially. And in the first example, it's the only other option besides the tilde to be the main operator. Now the material biconditional, the triple bar, abbreviates if and only if, or is a necessary and condition for. Textbook translation's always if and only if. Basically, it's two conditionals in one symbol. If somebody says A if B, that means that A will follow upon B, or B implies A. A only if B means that A implies B. A if and only if B abbreviates both of the preceding claims. It means A goes to B and B goes to A. It's a lot of information really quickly. One way of thinking about it is that conditionals or material implication is a one-way street. The implication goes one way. Biconditionals, by way of contrast, are a two-way street. The implication goes in both directions. Now, in each of these statements, the triple bar is the main connective. Again, take a look and try to figure out why that's the case. And before we go any further, we do need to talk about the concept of a well-formed formula, the WFFS. They're syntactically correct arrangements of symbols. For example, A horseshoes to wedge B is not well-formed. You can't really read that because you have two connectives right next to each other, two-place connectives, that is. However, the example in the green reads perfectly easily. And in the next example, A, B, and then parentheses, wedge C, is wrong on a lot of counts. You need some connectives between A, B, and the parentheses. However, the longer example underneath it reads perfectly well, and that's despite the length of the sentence in question. And in this example, we have a tilde in front of a wedge in the red. You just can't read these sorts of things unless they are well formed. Well, now you know a little bit about propositional logic and our 5 symbols that we're going to use to facilitate argument recognition. We need to go a little bit more into detail on the functions of these symbols. So the idea of functions may be a little exciting to some, and maybe not as much to others, but nonetheless, we're going to have a little bit of fun with them. The idea of a function is sometimes characterized as the idea of a black box. It's just a predictable output for any given input. For example, here I have the doubling function. Whatever number I put in, my little black box or my function just doubles it. Some people think about them as sets of sentences, like the ordered pair 2 to 4, 5 to 10, etc. This set of sets and so on could be the doubling function. So Frege was one of the people who helped develop this and apply it to the idea of truth, and Wittgenstein helped us compute these with tables. We're going to use both concepts here to get our minds more around our connectives. So when you have the negating function, if you put in an F, you get out a T. It's basically the flip-flop function. Basically, whatever goes in comes out the opposite truth value, in with one, out with another. Now, propositional logic is sometimes called truth functional because the truth of a compound expression is always an output of the truth value of the simple sentences you put in and the mapping job done by our definitions, our functional definitions of the logical operators that we just gave, the 5 logical operators. It didn't have to be that way. We could have had truth be a function of the meaning of sentences, or the length or complexity of sentences, or the context in which they were spoken. Nope, it's just going to come down in this case to the truth values of the propositions involved. That's the only thing our black box is going to operate on. So our negating function is pretty simple. You just put in one value and you get out the opposite. The negating function has a map to it, so to speak. You could say that whatever goes in, you get the opposite truth value for what comes out. Again, this is a truth function. Well, what if somebody said P dot Q or P and Q? Well, if both claims are false, and that's your input, well then you expressed a falsehood. And in fact, if your first claim is false and your second one's true, you still expressed a falsehood because P dot Q says that both propositions are true. The only way you're going to get a truth out of this little box is if you put in 2 truths like this last example. So the dot function or the conjunction function, if you'll permit me, gives you a true just in the first case on this map where P is true and Q is true. What about the disjunction? What about the wedge function, the either or? Well, if both of the things you said, either this or that, are false, 2 falsehoods, well, that should give you a falsehood for an output, right? And if only one of the 2 things you said is the case, well, that's pretty much all you claimed, right? So a truth and a falsehood combined should be able to give you an output of a true. What if you have both elements of your disjunction being true? In that case, we're going to go ahead and say if you said either P or Q and both P and Q turned out to be true, you still stated the truth. Now, that may seem a little bit weird, especially that top example. Can that possibly be right? If you say P wedge Q and both are true, can that be the case? I guess it depends on context, but we're going to say yes in this case. Now, it has to be admitted that there are some uses of the either or in the vernacular that defy this sort of usage. If somebody says either the train will arrive on track A or track B, they probably mean to exclude the idea that it's both the case that it will arrive on track A or it will arrive on track B. Or if somebody says either the Democrats will win or the Republicans will win the House, obviously they're probably trying to rule out the idea of both it being the case that the Republicans will win and the Democrats will win. On the other hand, there are some cases in which the more inclusive sense that we've used will be the case. If Wile E. Coyote says either I move faster or he gets away, you might say to yourself, that's true, Wile E., but maybe you'll move faster and he'll get away nonetheless. Both could be the case. So it has to be admitted that sometimes we do use the sense of either or that excludes this first possibility and says that only one could be true. That's sometimes called the exclusive disjunction, but in our case, we're going to stick with this table, and if we want to symbolize an exclusive disjunction, we'll just say A wedge B, and also the case that, well, not A and B at the same time. Now we have the material implication, where if you put in two falsehoods, you get out a truth. A falsehood and a truth will give you a truth as well. The only time with the material implication or the horseshoe that you get a falsehood is if the antecedent is true and the consequent is false. Now that's a little tricky, but here's the table for material implication, and you're just going to have to memorize the fact that when P is true and Q is false, you get a falsehood. True in all other cases. Now remember, the material implication symbol is the only one where the position of the two propositions matters, whether or not they're in front or behind the horseshoe. When you get falsehood for the consequent and falsehood for the antecedent, you get a truth nonetheless. Or if you get falsehood for the antecedent and truth for the consequent, that's still a truth. The only time you're going to get a false for an output is when truth goes in for the antecedent and falsehood for the consequent. Any other time, you wind up with a truth. So memorize this table. The output is always going to be true unless the antecedent was true and the consequent was false. It's very difficult to make this material implication or horseshoe symbol truth functional. The problem is, if we stick with the rule that I've just given you in the colored letters above, this diverges from ordinary uses because it neglects relevance of the antecedent and consequence. Relevance is not a truth functional concept. All we have to do to figure out or compute P horseshoe Q is figure out the truth of P and the truth of Q. Whether or not the content of P and Q relate to one another in any normal way is a different issue altogether. Now finally, I want to talk a little bit about biconditionals. Again, this is one of those cases in which the order doesn't really matter. If you get two falsehoods, well, then you were true to say that the two propositions had the same truth value. By way of contrast, if the two truth values diverge at all, you end up with a falsehood. And that goes for each of our ordered pairs here. So we can give you a little map of the biconditional function pretty simply as follows. The biconditional is true when the propositions have the same truth value, false otherwise. Using the rules that we've just discovered, you can easily compute even the most complex sentences. Just follow these simple steps. Assign truth or values to the individual sentence letters, and then put truth or falsity underneath the tildes immediately next to them. Compute for the operators joining those letters, and then work from the tildes on, or rather from the parentheses on outwards. Let's go ahead and try a few examples. Let's try to compute this one. First of all, let's start by putting our truth and falsity underneath each sentence letter. Assuming A, B, and C are true and D, E, and F are false, that looks like this. Now, we can easily compute the wedge claim next because that has to be true given our definition of the wedge. And finally, we're going to put an F under the main connective. Why? Because the wedge claim preceding it was true and what came afterwards was false. The rule for the horseshoe says that's the only time the horseshoe gets a falsehood under it. Let's try a more complex example. Assuming A, B, and C are true, this is what we wind up with, and D, E, and F are false. Now we can easily compute the connectives immediately connecting any two sentence letters. For example, the rule for B dot C gives us that we're going to get a truth there. And true for E horseshoes to A, because E is false and A is true. Now, what does that wind us up with at the end of the day? The rule for the horseshoe says this is going to count as true because everything to the left of the horseshoe is true and everything to the right of the horseshoe was true as well. Now this may seem a little intimidating, but go ahead and take it by the steps. Put your truth values under each propositional letter and then put your truth values, flip-flopping the truth values of each negated proposition. After that, you can start to work on your two-place connectives. D wedge F is going to be false because D and F are false. And since we have a tilde out in front of the parentheses there, that's going to flip-flop the value of our wedge claim. Now, B wedges to tilde A is going to be true because B is true and tilde A is false. That's going to give us a true for the dot claim for everything inside the brackets. Now, over on the other end, the horseshoe claim is going to end up true because F was false and so was tilde C. But then the tilde on the outside of those parentheses is going to flip-flop that value. The main connective, the horseshoe, thus winds up false. We had a true conjunction on the left hand of the horseshoe that implied a false negation on the right hand of the horseshoe. Try this one. Looks intimidating, but let's just take it by the numbers. Put our truth values underneath our individual propositional variables, and then underneath the tildes we'll go ahead and put the opposite truth value each and every time. All done with that, let's work on our two-place connectives. The triple bar gets a T because each side on each proposition on each side is true. We could put a falsehood for the dot, but then we'll go ahead and put a true for the horseshoe over here because A was true and so was tilde D. And over here, we're going to put a falsehood because C and E had different truth values. That's going to give us a true for the wedge, and we're going to flip-flop that for the tilde outside the brackets. The tilde outside of here is going to get a true, and consequently a true underneath the dot, and that's going to wind us up with a falsehood at the end of the day because we got different values on each side of the triple bar. Make sense? They don't get any more complex than this, but go ahead and just put your sentence letters, assign them truth and falsity, and go ahead and put truth and falsity underneath the tildes immediately preceding your sentence letters. After that, you can just work on things like the two-place connectives, like this dot, C dot tilde E is going to be true, whereas A dot tilde B will be false because A was true and tilde B was false. After that, because you have a negation outside the parentheses, you're going to flip-flop the value of that negation. Now you have a horseshoe claim here that you can say is true because the true conjunction led to a true negation. On the other end of the spectrum, you have a B wedge D. That's a true claim, but you have a tilde outside the parentheses, which is going to flip-flop that value. And over here on the opposite end, a false claim, tilde C, wedges to a false E. Two falsehoods gives you a falsehood. But that means that our triple bar is true because each side of the triple bar had the same truth value. What does that give us for our horseshoe in the middle? That gives us a truth. But since everything inside here is in the brackets governed by a tilde, well, that means we're going to flip-flop the entire proposition to a falsehood. See how that works? Well, you guys have done a whole lot of work here, and congratulations on mastering your operators and how to use them to compute the truth of compound sentences. Our operators are truth functional in that sense. We'll see you guys next time, and we'll put these to work on truth tables. Take care.